Okay, our second video on alternating series, and like I said, the test for convergence on alternating series is really straightforward. I don't think we need any more of that. What I do want to talk about in the second video, however, is something that's very crucial, especially anytime that alternating series comes up on a free response question. Uh, and it's sort of cloaked, meaning it's sort of disguised as to whether it's an alternating series. The thing that they're almost always asking for is error, because first of all, they want you to be able to identify an alternating series when you get to the AP exam. And then once you've identified an alternating series, they need to know that you understand how to find the error. Okay. Well, let's talk about exactly what a convergent alternating series looks like. And I gave you the visual before, right? As long as it's getting smaller, like its magnitude is getting smaller each time, you can go this way on the first one, and then this way. And each time it's getting smaller and smaller, and it's actually going towards a particular value, right? Well, here's the thing. Let's say we stop right here, and this is, of course, after six terms. So this would be a partial sum. So basically, this endpoint right here would be a partial sum for this alternating series. The error, since basically the next one goes back here, and you know that the next one is going to go past, whatever value it's actually sort of closing in on. This next move back, this seventh term, basically is the maximum error. So basically, it's really easy when you get to alternating series. You just have to figure out what the next term is, and that is your maximum error. And the way they put it in the book, I think, is something like, R sub n, which is the remainder, which is basically the real sum minus the partial sum, right? The difference. That needs to be less than or equal to, okay, the next term of the sequence, which is, A sub n plus 1 or B sub n plus 1 or whatever letter you're using for that particular series. So basically what it's saying is that the difference has to be less than or equal to the n plus 1th term if you've actually taken the partial sum to n terms. Okay, well, let's actually watch and see what that actually works out to be. Let's go ahead and let's say we have sigma. N is equal to 1 to infinity of negative 1 n plus 1 over n cubed, okay? And let's say, instead of giving you a definitive number of terms, what they are asking for is the number of terms required to approximate the sum of the series with an error less than. So you want this remainder, okay, to be less than or equal to 0.001, which basically means you want to get to a point where that third decimal place is not impacting the sum, the remainder, okay? So we know that if we plug in 1, we're going to get what? We're going to get 1. And then if we plug in 2, we're going to get 1/8. And if we plug in 3, we're going to get 1/27. We're going to get 4 and going to get 1/64. And then we're going to get 1/125. And then now 6 cubed is going to be what? Well, 6 squared is 36, and then 6 cubed is 216. Okay, 7 cubed, oh gosh, 343. It's late in the day here. I'm sort of 512, and then plus, gosh, is it 729? I think it is. 729. And then 10 cubed is, of course, 1,000. And 11 cubed is, well, whatever, okay? So basically, you need to find something that is going to impact the error less than this, okay? And of course, this right here, what is that? Well, that happens to be 1/1000th. So that happens to be 0.001. So if you want the sum of the series to have an error less than that, it needs to be the next term. It needs to be 1 over 11 cubed. Okay? Does that make sense? I hope so. Well, let's actually look back, because some of these actually require the calculator. Or even if they don't require it, it's probably a good idea to go ahead and use the calculator. Now, let's look at sigma. N is equal to 0 to infinity, -1 to the n, 2 to the n times n factorial. And they're already going to let you know that that is equal to 1 over root e. Now, we need to determine the number of terms required to approximate the sum of the convergence with a series with an error less than 0.001. Okay? Well, here's the thing. If you're basically just looking for that next term, which actually is less than that, so if you're looking for the error, which is less than or equal to 0.001, then really you're looking for the term, which is less than 0.001. You're looking for the next term. So if you find out that the 7th term gives you an error less than 0.001, then obviously you only have to go through 6 terms. Well, here's the thing. I went ahead and plugged that one in here to u of n, okay? I'm in the sequence mode, and this is my y equals screen. But here's the thing, since I'm looking at values at specific outputs, let's go ahead and press second table, and we'll go to here. And basically what we're doing is we're just looking for that first term. Now obviously when you plug in 1, you're going to get 0. Plug in 2, you're going to get 1/8. You plug in 3, and you're going to get -0.02083 repeated. All right, next. Now that right there, okay, e to the -4, means that the 5th term, okay, that means a sub 5 is equal to -0.000260417. Now, is that less than 0.001? Now, obviously, we're talking about magnitude, so let's actually plot the absolute value bars around there. And yes, the 5th term is the one that actually achieves an error less than that. So you only have to go through 4 terms in order to get within 0.001 of the actual value. Okay? Now, if we go ahead and let's go to here and let's actually do the summation in 0 to, and if the 0 term is the first term, okay, then obviously the second term, okay, n is equal to 0 is the first term, n is equal to 1 is the second term, n is equal to 3. So let's just sort of march forward to 4, okay. Oh, sorry, that's supposed to be this one. And we'll do the -1 raised to the nth, 2 raised to the nth, times n, and factorial. If you go to math right here underneath the alpha button and go over here to probability, it's number 4 right there. So let's go ahead and do that. Now, let's go ahead and change that into a decimal. Let's see how that compares to 1 over root e. And that is awfully, awfully close. It actually is that distance away. Because watch this. If I actually take the difference between these, it actually should be that. That's awfully close, okay? There's a little bit of sort of error in there because of the algorithm and stuff. But I hope that makes sense. What we're looking for is just if you find the term that gives you the error that you need, then it's all of the terms up to and including the one previous to that term that include your approximation. Okay, well, let's go ahead and let's look at one more. And I've plugged this one into that same y equals screen, so we'll get back there in just a second. 2n factorial is equal to cosine of 1. Okay? And of course, they mean 1 radian, right? Alrighty, well, I'm looking for the same thing. I'm looking for an error of less than 0.001. So let's actually go here, and we see that we have actually plugged that one into v of n. Okay, so if we go to that same screen, it should be over here. Okay, now that is just above 0.001, so it ought to be the next term. Okay, and so it winds up being a sub 4 is equal to 0.00002480159. Okay, and that right there is the error that you're looking for, because it's the first one that does not have anything in that thousandth, in that third decimal place to the right of the decimal. So this is your correct error that you're looking for, and therefore the summation is everything leading up to that. Okay? I hope that that's clear. We'll actually see how it bears out in terms of the power series and questions about Taylor and Maclaurin series as we move along a little bit. But basically, the summary for alternating series is that in order to find convergence and divergence, and of course it's only a test for convergence, it's not a test for divergence. If it actually doesn't satisfy the conditions, it's not necessarily divergent, it just doesn't actually, it's inconclusive and you have to go try another test. So you need to figure out, one, that a sub n plus 1 is less than or equal to a sub n for all n, meaning that the next term is always less than or equal to the preceding term. And you need to figure out that the limit of your a sub n is indeed going to 0. Because like I've said before, if it's decreasing in each term, but it's decreasing towards 1, that's not really helpful. It's got to be decreasing towards 0. Each term has to be closer and closer to evaporating into nothingness in order for it to be convergent. If both of these are satisfied, then your a sub n, sigma a sub n, is convergent, okay? And then the only other thing that you have to worry about is when you're dealing with error, the max error is the next term. Okay? So if you actually, if you actually find s sub 6, okay, and it's equal to, some number, s sub 7 is your error, is your max error. That's it. Okay, I hope that's pretty easy. Alternating series are pretty easy and pretty straightforward. We're going to get into a test that you're going to be using all the time in the next section, which is the ratio test, and we'll also discuss its cousin, the root test. We're getting pretty close to being done here. When we're done with 11.6, we will then move on to basically dealing with all of them all at once in 11.7. And 11.7 is kind of like a summary section of 11.3 to 11.6, where it gives you a whole smattering of series, of sigma notation series, and then asks you not only whether they're convergent or divergent, but asks you to pick which test you think is the best to use for that particular series. So that's actually a good sort of summation of the 4 sections, 11.3 through 11.6, and we'll get to that. But first, 11.6. So be on the lookout for that. Bye.